And I think you get the Fibonacci numbers somewhere in there. Like they'll be growing like yeah. So basically, roughly it'll be growing like one. So it grows like tau to the n, where tau is the golden ratio, which so it's roughly like 1.8 to the n, something like that. So that doesn't seem right, does it? Let's see. It's growing faster. Here it's growing faster than 2 to the n.
I think it skips a step, right?
What?
Well, it's going 2, 5, 13, so
Yeah.
it's going 2 in numbers, right?
Yeah, it's taking 2 steps at a time.
The dimensions growing faster than the Fibonacci sequence. Yeah.
Well, yeah. It's not a big deal though. Basically, it's growing like something to the n, where something is not necessarily an integer. It's not necessarily 2. Maybe that's the important thing. But it is still growing exponentially. That's important.
That is
But
important.
it's not necessarily 2, which means that we're gonna have like we can sort of quantum information, really interesting quantum states in this, but we have to do it in a funny way, possibly, because it's not just the dimensions are weird. These basis states are weird. You can't just treat them as bit strings. So actually, what people do usually is you embed your qubits into some dimensions of these. So let me just talk briefly about some physical issues. So physically, often what we say is these quasi-particles are local. You're going to somehow trap them with an electric charge or something when you're under 2-dimensional surface. And what that means is that if these themselves are local, then they have to be there. So because the environment can tell whether you have a 0 or 1. So what we're going to say is the topmost edges we're going to say are all 1s in our experiments. Okay, which means that in the 2-particle case, you're down to 1 dimension. The second thing we're going to say is that nature is able to observe the global charge. Charges, another word we use for this label. So nature can observe the global charge. So the global charge has to be fixed, either fixed to 0 or fixed to 1. Usually we're going to fix it to 0. And so actually we're not interested in all of these states. We're only interested in states where you have 1s at the top and the total charge is 0. So for example here, and in the Fibonacci model, we can just, I'll draw a line for 1, and I'll draw like nothing for 0, or I'll draw dots for 0. So instead of having to label them anymore. Okay, so I'm interested. So with 2 particles, there's nothing interesting that can happen. I have 1 dimension, but 1 dimension isn't enough to do anything. So the total charge is 0, but each of these guys is charged 1, okay, like that. That's the only thing that can happen. With 3 particles, so I have a 1, I have a 1, I have a 1. So this could be either 0 or a 1.